Hello, I present our paper, Scalable and Efficient Hierarchical Visual Topological Mapping, a work by Saravanabalagi Ramachandran, myself, Jonathan Horgan, Ganesh Sistu, and John McDonald. We build a hierarchical topological map using only images. Compared to metric maps, topological maps offer a simpler and more compact representation that occupies less space. Although indexing techniques and hierarchical representations can be used in metric maps, we can build more scalable and efficient maps of trajectories that are several kilometers long using topological maps. We build on top of the existing HTMap technique, adding a number of improvements and optimizations, and more importantly, we propose the use of learned global descriptors to group similar images into locations. Larger dots are locations, and smaller dots of the same color are images that belong to that location. And we use different colors to represent different locations. As such, any vision-based mapping technique relies on a visual loop closure detection system, where previously visited places are recognized using content-based image retrieval techniques. As new images get processed, location-level loop closures are proposed based on the similarity between the global descriptor of the current image and that of the locations in the map. The loop closing image candidates are then searched only within these proposed locations. Through our experiments, we find that the characteristics of the global descriptor significantly affects the distribution of images within locations, which in turn affects runtime. In the original implementation of HTMap, a discrete Bayes filter utilizing an evolution transition model to compute a belief distribution over a set of previously processed images is used to avoid spurious image loop closures. We identify and fix a number of problems related to the accumulation and dissipation of energy over time by the evolution model. We ensure that the posterior distribution distributes its belief uniformly across all poses in the absence of measurement updates. The updated Bayes filter resulted in an efficient mapping and localization process. More importantly, we adapt the framework to utilize learned global descriptors. In our experiments, we compare 4 global descriptors, phog, netflat, lost, and divvae, which are state-of-the-art in each paradigm mentioned. We critically analyze the characteristics of the global descriptors and how they impact scalability and efficiency in a hierarchical setting. As part of our extensive analysis on the characteristics of the global descriptor candidates, we compare their similarity matrices. As the distance function is commutative, the similarity matrices are symmetrical along the principal diagonal, and hence we combine the upper and lower triangular matrices for a better comparison. Too many similar descriptors result in many false positive locations, while too many distinct descriptors result in poor aggregation of images. We postulate 2 important characteristics for a global descriptor to function efficiently in a hierarchical setting: continuity and distinctiveness. The effects can be seen magnified in longer trajectories like St. Lucia. Here, we map St. Lucia using 6 different global descriptors. The new node threshold determines how many locations will be there in the final map. Hence, we repeatedly run the mapping process, altering the new node threshold such that the map yields 100 to 700 locations. Since the bounds and the scale of the new node threshold vary significantly for different global descriptors, we plot the recall at 100% precision against the total number of locations instead. Each dot in this graph represents a mapping process with a certain threshold, mapped against the total number of locations obtained. The recall at 100% precision only changes negligibly among the evaluated candidates.
showing that all global descriptors propose sufficient loop closing candidates without suffering any considerable drop in recall. Upon closer examination, we observed a significantly imbalanced distribution of images across locations
correlated with total runtime.
Maps with fewer locations, comprising a very large number of images, diminish the advantage of the hierarchical approach and hence impair the search efficiency, whereas an increased number of locations, each comprising only a very few images, leads to more location searches. Therefore, achieving optimal performance requires avoiding both overpopulated and underpopulated locations. The max intra-cluster distance, the new node threshold, affects the location cluster cohesion and separation. That is, it determines how many locations are formed and how populated the locations are. Usually, a small value for the threshold results in a map with large number of locations, and a larger threshold yields fewer locations. However, we note that this balance is also influenced by other factors. The location image aggregation affects the loop closure proposals, and the loop closures affect the image aggregation dynamics for subsequent images, which in turn affect further loop closures. Consequently, it is possible that a slightly higher value of the threshold yields
more locations instead of fewer.
Further, paradoxically, the generation of certain novel locations and subsequent loop closure misses can lead to an increase in the overall recall in certain instances, which can be attributed to the dynamic hierarchical structure.
Here is an example showing a portion of the city center trajectory visualized in Odovis. The car moves from left to right, and the dots at the bottom represent the poses from the first traversal, and the dots at the top represent the poses from the second traversal. Poses that belong to the same location are in the same color, and the image loop closure proposals are shown in red. We run the mapping again with a slightly lower TNN and expect to obtain more locations. However, counterintuitively, a loop closure miss resulted in the formation of fewer but cohesive locations, which in turn resulted in a slightly higher overall recall. Although this might not happen as often, it provides us with useful insight to understand the dynamic hierarchical structure. In the histograms presented, locations with fewer than 5 images are highlighted. This is significantly higher for NetVlad, given that out of 101 locations, 65 locations have very few images. We argue that NetVlad produces disproportionately large number of locations with fewer than 5 images due to the lack of sufficient continuity. In our experimental evaluation, we find that DiffAE produces significantly lower false positive locations. We attribute this to the distinctiveness characteristics exhibited by DiffAE. These two characteristics in turn enable achieving substantially lower runtimes. We note that the runtimes do not include the descriptor compute times. DiffAE performs up to 2.3 times faster than the second best global descriptor, NetVlad, and up to 9.5 times faster than the handcraft descriptor PHOG on St. Lucia, while maintaining the same performance, achieving recall values similar to that of other descriptors. We further record and compare the compute times for each global descriptor. For fair comparison, Python implementation of the descriptor models were used. We report the compute times for the maximum batch size in a batch processing setting, in addition to reporting compute times for batch size of 1. While one might contend that learned descriptors demand dedicated hardware, it is noteworthy that GPUs are increasingly accessible. Furthermore, advancements in technology have led to the production of more cost-effective, energy-efficient GPUs, making them a practical choice for a wider range of applications. As a result, the entry barrier for implementing learned descriptors is gradually diminishing, contributing to their broader adoption in various computing environments. DIPVAE is compact with an embedding length of 128 and is significantly faster to compute compared to other global descriptors. We conclude continuity and distinctiveness to be crucial characteristics for an optimal global descriptor that enable efficient and scalable hierarchical mapping.